don't know, my collaboration with Claudia Schembauer started because we were passing notes at the back of a lecture. So I encourage this behavior.
Right. Andy, anything else I need to know to, I haven't introduced people in a while. Do you want to remind me what I need to do?
I don't think there's too much you have to do. We used to briefly go over the kind of ground rules, and I guess since you've just discussed having people just talk freely in the chat and speak out with their questions, maybe you could tell people to do that. Other than that, I think there's nothing you really have to do.
Okay, easy enough.
Oh, maybe you have to push no, there is one thing. You should push the record button when
yeah,
when you start.
The record button is, yeah. So Theo, we'll start in about 30 seconds.
Okay.
If you're ready.
I'm not going to get more ready.
Right. But we want to wait for, we don't want to start before the hour.
But folks are still coming in.
Yeah, people are coming in. Okay, so it's a great pleasure to resume our Western Hemisphere colloquia. I think everybody pretty much knows the system. You're currently muted, but you're able to unmute yourself if you want to ask a question. Better yet, Theo suggests that people can post questions to the chat, and we can all discuss it behind the scenes. And if you want to interrupt, just go ahead and interrupt with a question. There will also be a question and answer session at the end after 60 minutes. So it's a great pleasure to introduce Theo Johnson-Freyd, who will talk about semi-simple higher categories.
So thank you very much. It's a great honor to speak here. I think I'm not the first person to say it's an honor to speak in the Western Hemisphere. So, right, I'm going to talk about semi-simple higher categories. And if you want to look over the slides at your own rate, I've posted them on my website. The most important thing, and everything I'm going to tell you is joint work, but it's joint work. I really want to draw your attention to this word in progress. I'm going to tell you things that we have. Pretty much every statement I'm going to make means that is something that we have a kind of idea or outline of how to prove, but we probably haven't written up details. So that's a kind of blanket disclaimer for this talk. So my goal is to tell you about semi-simple higher categories, and I'm just going to dive in and give the definition of a semi-simple higher category. And then most of the talk is going to be, I don't expect you to kind of process the definition like that. Most of the talk is supposed to be a kind of survey of some of the things that, that this definition entails. So the first thing I'd like to do is remind you what a semi-simple lower category is, what a semi-simple one category is. And that's the part of the definition that's written in black, or I guess black and light blue. A semi-simple category is a category which has direct sums. It has the feature that every idempotent has an image. So an idempotent is an element, sort of an endomorphism, which squares to itself. That's what that's the definition of an idempotent. Having every idempotent have an image is a very, very weak type of having kernels and co-kerns. So there's a very weak type of very weak restriction. But then I make it very strong. I ask that for every object in my category, I have a semi-simple algebra living at that object. So that's the definition. That's a kind of very standard definition in 20th century category theory, or rather, it's the usual definition in 20th century category theory is much longer, and then you prove that it's equivalent to these properties. And the n-categorical version of it is unnatural generalization to higher categories. So the natural generalization is, I'll just repeat the definition. An n category is semisimple. Well, maybe a linear n category is semisimple. When it has direct sums, okay, if you know what a direct sum in a one category is, you can work out what a direct sum in an n category is. Direct sum is always a type of addition. And you, somewhere in the definition of a direct sum, there's usually a plus sign somewhere. You just make that a direct sum sort of inductively. And also every idempotent has an image. There's a really nice generalization of idempotent that I'm not going to dwell on. You can trust me that it feels like idempotence. It feels like working with the word idempotent is there's lots of words for idempotent. Idempotent is also called like a projector operator. And there's a very nice definition of idempotent that we worked out with David Reutter that's an n categorical version of idempotent. Again, I want a local semi-simplicity. Well, in an n category, the basic definition of an n category, my n categories, I'm not going to assume, like, you can work naively with n categories for the purpose of this talk. An n category is like a one category, except instead of having, you have some objects. In a one category, you have some objects and you have some morphisms, some sort of directed paths from object to object. And if you have some collection of paths, there's a way to compose them. In an n category, it's just the same. You have some objects. Instead of having a set of paths between any two objects and a way of composing them, you have an n-1 category of paths. So when you unpack that, you find that there's that n-1 category has its own set of objects and paths between those, which are the paths, and then paths between paths. And there's a sort of tower of structure there. And so I just ask that all of those n-1 categories that live between objects in my n category are semi-simple, and they're semi-simple kind of, the algebra becomes monoidal n-1 category. Monoidal just means having a way of multiplying, just like an algebra. There's another part of the property that I want to add that turns out to be the correct definition, which is to add that every morphism has an adjoint. And this is the notion of adjoint of morphisms is on the one hand comes from the notion of adjoints of functors. It's some weak version of being invertible. And it turns out that that's a natural thing to add to the word semi-simple. And that's the definition. Oh, and I sort of am getting myself out of order because I wanted to say a little bit more about just to sort of flag the type of feature of our definition of n categorical idempotent with Guyot, that's joint with Guyotto. Let me add some well, anyway, as I said, this was work of mine and Guyotto's in the general case. But the basic idea of semi-simple n categories, so this was from like 2019, and then that was used, except it wasn't because there was some time travel, and this was used by Douglas and Reutter in 2018, who actually beat us to the punch for a lot of the notions. So that's worth giving some credit. Anyway, so the n categorical definition of idempotent, which I said I'm not going to dwell on, but I wanted to give you a sense of what goes into it. Instead of having an isomorphism between, so it's a map from an object to itself, you don't ask that it squares to itself. Rather, you ask that the square of the map kind of contain the map P as the image of an idempotent one dimension lower. And so again, this is an inductive procedure. And also there's some coherence properties that you can ignore, or that higher categories theorists would know how to fill in, that relate kind of, well, if P squared has something to do with P, then P cubed has something to do with P in two different ways. And so you relate those and you build up from them. That's the general definition. That's the structure of the definition. And I could just sort of end my talk here because I've given you the definition and you can go forth. But I'm instead going to use the next, I guess, 52 minutes to tell you some of the properties that this definition leads to. So, and Let me sort of tell you some examples in very low dimensions. And already to kind of give a feel for it, one of the punchlines I want to tell you about is that semi-simple categories end up feeling very much like doing algebraic topology. They feel like homotopy theory. And so I'd like to tell you what that feels like in very low dimensions. So to start, let me remind you what it feels like just in a one category. And maybe the first example of a semi-simple one category that anyone ever meets, well, I don't know, the first example that many people meet is the category of representations of a finite group over a field of characteristic not dividing the order of the group. And so in particular, if you say are in a field of characteristic not 2, then you can ask what does the representations of the group of order 2 look like? Well, there are lots of representations of the group of order 2. You can write down any matrix which squares to the identity. But one of the first structure theorems you prove in undergraduate linear algebra is that you can often diagonalize matrices. And in undergraduate algebra, you prove sort of structure theorems for when you can diagonalize. If you have a matrix which squares to the identity, it always diagonalizes. So it'll square to the identity, so its eigenvalues will either be +1s or -1s. And if you have kind of a bunch of +1s and a bunch of -1s, I know that's just sort of evaporating, then that gives you a direct sum decomposition of your matrix into sort of pieces. That's what a diagonalizing a matrix does, is it's a direct sum decomposition. And the fundamental pieces, the irreducible representations of Z mod 2 are either, well, there's the trivial representation, where your matrix is just the matrix, the 1-by-1 matrix +1. And there's the sign representation, where your matrix is the matrix -1. And then those representations have endomorphisms. You can multiply by any scalar. And these two representations, from the perspective of the category, have nothing to do with each other. They're just disconnected in the category. And then the whole category is built by taking these two basic pieces and adding and taking sums of those. So the end result is that this category just basically feels like a set of order 2. It doesn't feel like a very interesting object. It just feels like you could kind of remember it just by remembering that it has 2 elements in it. You didn't have to remember where it came from. It has two elements, 2 objects, 2 simple objects. Over an algebraically closed field, excuse me, over an algebraically closed field, so over the complex numbers, if you like everything, I'm gonna keep. I could have just written my whole talk, and you would have gotten everything out of it just by pretending over the complex numbers for my whole talk. That would be fun. So over an algebraically closed field, every semi-simple one category feels this way. Every semi-simple one category, at least every one that has some local finiteness conditions, feels like a set. There's really not much interesting geometrically in semi-simple categories. Non-semi-simple categories are really rich geometrically. Semi-simple categories are not rich geometrically. And more precisely, when you account for maps, it's not literally true that there's an equivalence between semi-simple categories and sets, but it's almost true. There's a little bit of like characteristic, maps to characteristic classes. And if you want to ignore me for the rest of the talk, there's a fun game to figure out what every semi-simple category over a non-algebraically closed field feels like, and you'll see this showing. So that's what one categories feel like. Now, you might have thought that semi-simple 2 categories feel the same way, that they also have this property that it just feels like a set. And you might have thought this because you might think a vector space also feels like a set. It just feels like the basis of it. And maybe that's the pattern in general, but it turns out not to be true, not quite. And so an example I want to give is the semi-simple 2 category of 2 representations of Z mod 2. A representation of Z mod 2 was a vector space with an endomorphism that squares to the identity. A 2 representation of Z mod 2 is a category with an endomorphism which squares to the identity in a categorically coherent way. And at least if you look at kind of finite dimensional 2 representations, then the collection of all of those feels as follows. I've drawn a picture of it where I've drawn all of the simple things. So the whole category is built out of direct sums of this picture. So let me spell it out for you. There are 2 simple representations. There's the trivial representation, and there's the rank 1 free module. It turns out that it doesn't, the rank, unlike in the one-dimensional case, in the 2 categorical case, the rank 1 free module does not decompose as a direct sum of like a sign representation and a trivial one. So it's more like kind of if you study it over a field of characteristic 2. The trivial representation has its endomorphisms are a copy of the one-dimensional representation theory, of the one categorical representation theory, which we already described. That had 2 simple objects, like it had a trivial rep and a sign rep. So I've labeled those 1 and X. But there's also a way of composing. Well, the composition is the tensor product of representations up here. The sign representation multiplies with itself to the trivial representation because this was the representation of the matrix acting by -1. And the tensor product of matrices is like the multiplication of entries in the matrix. So you got a kind of X squared is 1 as endomorphism. The rank 1 free module, if you work at its endomorphisms, it turns out it also has 2 simple endomorphisms. I've called them 1 and I've called them Y. The whole category is a category called vec Z mod 2. It's equivalent to the category rep Z mod 2. And so you have a formula like Y squared is equal to 1, or is isomorphic to 1 anyway. These are morphisms in a 2 categories, so it makes sense to ask what are isomorphisms between them. The weird thing here that you see is that these 2 objects, they're both simple, but they're related by morphisms. It turns out that the category of morphisms in either direction is a copy of the category of vector spaces. There's a unique simple morphism in either direction, and it's not invertible.
Theo,
it turns out that yes, but let me just finish the sentence that if you take this object and go around, it splits as a sum of 1 and X. Yes, Greg.
So vec Z mod 2, is that vector spaces over the field?
Sorry, vec Z mod 2 means Z mod 2 graded vector spaces with the kind of multiplication, which is just adding the gradients.
Causal rule? When you say a rank 1 free module, you mean a free module over this category? As a module? I'm not quite sure what you mean by a rank 1 free module. It looks like the category is acting on that.
Yes, so you asked me 2 questions. First of all, this is only a monoidal category, so the causal rules don't play a role whatsoever. This category is equivalent to the category of kind of rep Z mod 2. It's monoidally equivalent to that. The second answer was, sorry, I called it a rank free module because you know that rep Z mod 2 is the modules for a ring, which is like C adjoin X mod X squared is 1.
Oh, so you mean a module?
And under that type of equivalence, this is like the 2 modules for, it turns out, 4 vec Z mod 2. And I mean the rank 1 free module in the sense of module theory.
So just a remark maybe for Greg, I think in condensed matter, these will be called smooth boundary conditions and hairy boundary conditions. And the trivial is hairy and what he's calling the rank 1 would be smooth.
Great. I don't remember which is which, but I agree with the rest of the sentence. I confirm the rest of the sentence and I cannot deny which is which. Thank you, Kevin. So this is a thing I want to say, I'll say again, which is that there's these objects, they're both sort of, well, I haven't told you what a simple object are, but it turns out that in 2 categories, it happens a lot that simple objects have non-trivial maps between them, non-invertible maps between them. So let me tell you that now. So there's a natural notion of simple that for 2 categories. In a 1 category, or actually in a 2 category, an object is simple when all of them, when there's lots of definitions of simple. For instance, you can say an object is simple when it has no sub-objects. Another definition is that an object is simple when every map out of it is an injection. Every non-zero map out of it is an injection. And in a semi-simple category, every object decomposes as a sum of simples, just like it does in a semi-simple one category. There's a statement that I've called Schur's lemma, and I forgot to write up the one categorical Schur's lemma. So let me compare this with the one categorical Schur's lemma. Says that the point in a one category, well, I told you every one category just feels like a set. And what that tells you, the point there is that in a one category, any non-zero map between simples is an iso. That's the thing that fails in an interesting way when you categorify. Instead, when you categorify, what turns out is that if you have a map between simples, which is not zero, it's not an iso, it's almost an iso. So what you can do is you can almost split it. You can realize if you have a map between simples, then you can realize X, well, actually anytime X is, if there is a simple that ended and you have maps between it, then you can realize X is the image of a projection sort of on the domain. So, and vice versa if they're both simple. So any map between simples, each one of the two objects is like the image of a projection on the other one, the image of an n-item potent. And the difference in two categories is that n-item potents are a little bit different from ordinary item potents. A side effect of this is that although there can be non-trivial maps, non-invertible maps between simples, it turns out that any composition of non-zero maps is again not zero. And this is a slightly weird feature of semi-simple. It was a slightly surprising to me feature anyway of semi-simple higher categories, that compositions of non-zero stay non-zero, because that doesn't always happen in rings, for instance. And so there's a notion of equivalence of objects, which is weaker than categorical equivalence. And the notion of equivalence is, we call it Schur equivalence, which is that two simple objects are Schur connected if they can be connected by a non-zero map. And there's only a notion on simple objects. And then you can talk about the equivalence classes for that equivalence relation. So just to remind the example, here's my picture of, I drew a completely explicit picture of this two category. Here's two simple objects. They're not categorically equivalent. There's no isomorphism between them, but they're still Schur connected. They're still weakly equivalent in this weak sense.
Theo, could you give an example of a two-item potent in this example?
Could I give an example of a two-item potent? Yes, if you take the object 1 plus x, that's a one morphism from this object. So you take this object, take the one morphism 1 plus x. That's a one morphism from this object to itself. When you square it, you get 1 plus x plus x. If you work out these fusion rules. So Greg asks, so if p is 1 plus x, and you look at p squared, which is kind of 1 plus x, and there's a natural way to map that to 1 plus x, which is that you just take 1 and map it to 1 in both cases, and both x is mapped to x. And there's a natural, in fact, there's a natural way that 1 plus x lives as a direct summand of 1 plus x plus x. It lives kind of diagonally in this 1 plus 1, and this 1 lives diagonally in this 1 plus 1. This x lives diagonally in this x plus x. That's an example of a two-item potent, because I told you that the rule was not that p squared is equal to p, but that p squared contains p as the image of a projection. So that's an example of a two-item potent at this object. And when you ask, what is the image of that 2 idempotent, it turns out that it's this object. And these are turn out to be the projection and injection of the image. So it's not like you're used to in 1 categories where objects only have identity idempotents. Okay. So there's this natural notion of equivalence, and I'm going to talk about the components of C as the simples modulo this notion of connectivity. And I want you to think of these as like the path components in a space. And the reason I want you to think of these as the path components in a space really comes from looking at this picture and taking it seriously as if it's a picture of a space. As soon as I tell you what the components of a space are, you can talk about the higher homotopy sets of a space. So let's take a category, take an N category. Let's pick a point in it. So let's pick an object in my N category. Let's rather pick a simple object. That's called the pointing of my N category. And I'll call the category connected when, like in the example, there's only 1 component. Then I can define the loop space at that base point, which is just the endomorphisms of the object. Sorry. So these are the paths from the object to itself, is what this loop space is. Turns out that this loop space in this pointed connected case determines this loop category as a monoidal category. There's a way, of course, of composing paths, so it's monoidal. Turns out it determines the whole category, so you didn't lose any information from doing this. And also this this category has its own pointing. It's a monoidal category. It's an algebra type category, so it has the unit element. And so you can do iterated loop spaces. You can take kind of loops k many times. And when you take loops k many times, this will be some semi-simple n minus k category. And you can take its Schur components, and I'll call those the homotopy set, the kth homotopy set of C. And I want to warn or maybe point out 2 features of this. First of all, there's no reason for these homotopy sets to be groups. This is not like regular topology where you have homotopy groups. And that's because the maps in my category don't have to be invertible. So they're not a group. They are the basis for a ring, and they're the basis for a fusion ring. It's like very close to being a group, but they're not a group. The other thing I want to warn is that in algebraic topology, we get used to the idea that if you take different base points in the same component of a space and ask for the homotopy groups of those base points, the answers we get are isomorphic. And the isomorphism is given by conjugating by the path between those 2 base points. This doesn't happen in higher categories. It's pretty easy to give examples where different simple points in your category give you radically different homotopy sets. So the pi k's can really do depend sensitively on which point you pick as sets. There's still a weak sense in which they don't, which is that the reason why the homotopy sets, the homotopy groups of a space are isomorphic is because in fact you could take the whole loop spaces and identify those by conjugating by a path. Well, these monoidal categories aren't equivalent in general if you pick different base points, but they're Morita equivalent. They're the next best thing after being equivalent. So it's a kind of quantum version of equivalence. And in fact, like, maybe if any of you who might have learned about, so maybe in quantum geometry, in non-commutative geometry, Morita equivalence is used a lot as the right notion of equivalence of quantum geometric spaces. And that's also showing up here. As soon as I know what it means to talk about the homotopy sets, I can also talk about finite spaces. So I can ask whether these sets are all finite or not. And these are only really good for k less than sort of up to, if I'm in an n category, I only have the homotopy sets up to n minus 1. There's a sense in which the nth homotopy set is the ring k, but that's the ground field that I'm working over. I don't know how much I want to take that as serious. There's no data in I don't know above. The data in the homotopy sets is from 0 through n minus 1. And I'm telling you this because I really want you to think of these as like spaces with homotopy in degrees 0 through n minus 1. And I want to make this really serious. I want you to think of these as quantum homotopy types. That's what it turns out semi-simple categories feel like. I told you already that semi-simple one categories felt like sets. And what I'm telling you now is that semi-simple n categories feel a lot like, so sets are spaces, from the perspective of algebraic topology, a set is a space with only homotopy in degree 0. Because from the perspective of algebraic topology, there's no difference between a point and Rn, for instance, a point in any contractible space. As an example, so I want to give another very general construction, and then I'll tell you I'll kind of emphasize this quantum homotopy type idea that we have, which is that if you did have a finite homotopy type, meaning a space, so this is a topological space, all of whose homotopy groups are finite, and it's sort of sufficiently high homotopy groups are all trivial, then you can linearize it. And more generally, there's a way of linearizing spaces equipped with, this is a homotopy theorist's way of writing a class in the cohomology of the space. So if you give me this data, I can produce for you a linearization of it. And it'll linearize to some semi-simple n category. And this is true in characteristic 0. It's true, I think, when the characteristic doesn't divide the orders of any of these groups. So that's a way of producing sort of quantum these semi-simple categories. And the examples I gave you are actually come in this way from the space RP infinity. Moreover, the linearization has a sort of, if you pick a base point in your space, if you pick any points in your space, then that picks a point, an object in its linearization. And you can take the homotopy sets at those base points. And if your space also doesn't, well, every n category I told you really only has homotopy up to degree n minus 1. If your space also only has homotopy up to degree n minus 1, then the homotopy sets are the same. And you can recover the space with its cohomology class from the category. So this is sort of, what I'm telling you is that semi-simple categories, or rather pointed semi-simple categories, contain spaces as really as like a sub-collection. And on going the other way, what we've learned over the last year or so is that really every semi-simple n category has this flavor where it feels like a space, it feels like it comes as linearizing a space with homotopy only in degrees n up to n minus 1. So it feels like an n minus 1 type. But they feel like a slightly quantum version of n minus 1 type, where when you compose paths, you don't get other paths, but you get kind of superpositions of paths. Now, all the constructions you'd ever want to do in algebraic topology, where you attach cells, or you build a space by attaching cells or by composing things, all of those constructions I feel like, are like in the ordinary topology, but you have to include direct sums and you have to allow images of idempotency. And then that really is what these spaces end up feeling like.
Theo, could you say a little more precisely what you mean by linearize?
I hadn't intended to.
Okay, so is pi k of c equals pi k of x part of the definition of linearization?
Sorry, the sound cut out for a moment. I think you asked, is pi k of c equal pi k of x a part of the definition, but I'm not sure if
that's exactly what I asked, yes.
Okay. No, a priori, that's not it. So for people who, well, I'll say what sort of a way to think about it. There's multiple sort of ways to do it, but one way to give the construction of linearization is to say that what the data of this map is it's selecting. If I gave you a map if I gave you a space with a class of degree 2, that would be selecting a line. No, if I gave you a space with a class in degree 1, that would be selecting a line bundle. And you could ask for the space of sections of that line bundle. And if I gave you a space with a class of degree 2, that would be giving you a gerb. And I could ask you for the category of sections of that gerb. Okay. And there's a sort of higher version of that.
Okay.
So if those are useful words for you, then that's the definition.
Yeah,
if those aren't,
Thank you.
But yeah. Another term I could have bandied around was I could have called this a digraph-Witten type construction. You could think of this class as being some sort of digraph-Witten action, and you could think of these categories as arising from sort of some generalized digraph-Witten construction.
There are a couple of other questions in the chat if you would like to look at them.
Can you tell me which ones you're?
Sure.
I promised I would not look at the chat in case people wanted to discuss with them themselves.
Ulrich Penning is asking if the homotopy sets of a semisimple and category C are groups. Does it come from this construction for space X?
If they are groups, does it come from this construction? I don't believe so.
I think you can already in dimension 1 for fusion categories, you have fusion rings that are groups, but where the fusion category does not arise in this way. No, wait, is that right?
No, that's not true.
No, that's wrong. Yeah, exactly. Okay, that's
exactly not true.
Yeah. So then
this is a good question that we have to think more about. My intuition is no. My intuition is that it's possible to be a group at the level of homotopy and not a group at the level of categories. But I don't have an example off the top of my head, sorry.
Okay, do you want another one?
Sure.
Okay, so this is from Ezra Getzler. The example that you gave is a nilpotent homotopy type. Does this work as well for non-nilpotent finite homotopy types?
Ezra, I had only intended to give this for finite homotopy types.
I think he's asking whether nilpotence is essential.
This works when there's homotopy in degree 1, and then it's just a finite group. So examples are that if I take the trivial, well, an example is that if I take just a finite group and take its corresponding classifying space, that's an example of a finite homotopy type whose only homotopy is in degree 1. It's as far from nilpotent as possible. And if I linearize it, then I get the n category of n categorical representations of that group. So this really, it's really not, anyway. So the second half of my talk was, that I wanted to tell you about was sort of some applications of this and sort of some more moving more towards quantum that in the back of my mind have sort of a quantum field theoretic flavor to them. And well, let me just tell you what I want to tell you. So the idea for this that I want to tell you is that where I got into the game was because one of the ways semisimple categories can arise is they can arise as topological operators in quantum field theories. And either if you think about them as operators, or if you just think kind of because you know some category theory, whenever you have a k-morphism in an n category, k-morphisms in n categories are are things that want to be inserted. You want to draw them as codimension K surfaces, on codimension K surfaces. K-morphisms sort of feel that like, well, they sort of feel K-dimensional and they sort of feel co-K-dimensional under kind of a Poincare duality. So in particular, if you have an invertible K-morphism, invertible K-morphisms are things you really want to, well, yeah. So now you can ask kind of, when can you really put a K-morphism on a surface? Do you need, like, what extra data do you need to really interpret that? And the answer for invertible K-morphisms is that you can put an invertible K-morphism along a surface if the surface is normally framed. The normal framing basically tells you the direction the K-morphism goes, and it's kind of a Poincare duality thing. So it's the direction kind of across the surface, because the surface, the codimension K surface is like the interface between the source and target of the morphism. A normal framing is by definition a trivialization of the normal bundle. You take the normal bundle to your surface, and you want to make it trivial. An example of this that matters in quantum field theory is if you take your K-morphism and insert it along a sphere. Excuse me, my screen has decided to make itself dark, and I'm going to try to, I don't know why. Well, it looked dark to me. It kept getting darker. Sorry. Maybe it's sort of doing some funny Apple thing.
It looks fine to us.
Okay, it looks fine to you. Then I'll just push forward. So you can, but the point is that you can always insert K-morphisms like on normally embedded hyperplanes. And the question is, when can you insert K-morphisms on curved surfaces and on surfaces with topology? And the answer is that you need to have a normal frame. So something you could do is you could take any morphism in your category and put it on sort of a hyperplane. That you're always allowed to do. And you could take an invertible morphism and put it on a sphere. And you could make these of complementary dimension, meaning that the dimension of the sphere and the dimension of this hyperplane should together add up, I guess, to one less than the ambient dimension, so that there's one dimension that they could look. And I'm hoping that the picture is clear. This is a picture going on in 4 dimensions. Here's a one manifold puncturing, passing through the middle of a sphere in 4 dimensions. So there's like a line with a sphere sort of linking it in 4 dimensions. And if X is invertible, then I'm allowed to put it on a sphere. And the normal framing I'm going to take, I'll call it the standard normal framing. It's the normal framing that sticks out. That arises from sort of boundary, the sphere as the boundary of a disk. And this ends up being the kind of a version of the way of X conjugating Y. If you thought in sort of just in like, if these were just sort of, if you're in very low dimension, if you just had n was 1, then you were just looking at R1 as your ambient space. So this was a picture in R4. But if I compared it to R1, then here I'd put Y, and here I'd put X on a 0 sphere. Well, the 0 sphere has a positive sign and a negative sign as the 2 sort of elements. So it ends up looking like you put X on one side and X inverse on the other. And you're seeing the conjugation action. And you can already see that it mattered that X was invertible to be able to do this. But this is a category theorist's way of understanding what it means to talk about invertible extended operators as a type of higher form symmetry in a quantum field theory. And I know a lot of people in the audience are kind of coming from a quantum field theory world and know this wonderful work on higher form symmetries by Gallardo, Kapustin, Seiberg, and Will, for instance. The thing I wanted to tell you is that this doesn't work a priori when X is not invertible. So if X is not invertible, you can ask the same question. What does it mean? What do you need to do to insert it along the surface? And there's an answer given by by Jacob Lurie in his cobordism hypothesis paper. So you can actually read this this is sort of spelled out in section 4 of Lurie's TFT paper. The answer is that in general, if you had a K-morphism, to put it on a codimension K surface, if the morphism is not invertible, then you need more data than just a normal framing. You also end up needing a tangential framing. You need to frame your surface. So you need to trivialize its tangent bundle in addition to its normal bundle. And you have to have a compatibility which is extra data in general, that the sum of these two data has to be kind of the ambient trivial framing of the sum of tangent plus normal bundle. And usually spheres can't do this. So usually you cannot take a random morphism, a random element in a category and insert it along a sphere. Nevertheless, if you have what we proved was that if you have a simple object, and if you're in a semi-simple ambient world, then there is a way of doing this. That there's in fact a canonical way to insert simple objects on spheres, which goes beyond the cobordism hypothesis a little bit. The way it feels like is it feels like the morphisms, or at least the simple morphisms in semi-simple categories, are slightly more dualizable, slightly closer to being invertible than a non-invertible morphism in a category has any right to be. This is a canonical thing to do. It really only works for simple morphisms. If you ask me what to do with non-simple things, well, every non-simple thing breaks up as a direct sum of simple things. So you could just say, well, I'll just insert the sum, I'll take the sum of the insertions. That's not a good answer because it's not multiplicative. This is something that really works for simple morphisms and not for sums of simples, and so not from products of simples either. The upshot of this is it gives a way for simple morphisms to kind of act by conjugation, even if they're not invertible. And so this is, if any of you are kind of trying to figure out, if any mathematicians are trying to figure out what the kind of actual definitions in this kind of generalized symmetry or categorical symmetry or non-invertible symmetry is, this is one of the things that is. Yes,
Theo, I had a
Kevin.
question. So if we were in relatively low dimensions and we could talk about things that are pivotal and spherical, in that case, would there be any obstructions to putting these things on surfaces, or would it just work because of the pivotality?
Great question. So if your ambient category is, so I think it still needs extra data. I'd have to think a little bit. I think I still need a little extra data that's kind of a relative pivotal structure on the morphism, in addition to a pivotal structure on the ambient category. But yes, so there's another thing Kevin points out, that sort of behind the scenes for the rest of the audience, what Kevin points out, that often categories arrive to you with more information than just being a semi-simple category. And that extra information would be a monoidal way of wrapping objects on surfaces or spheres, which is in general extra choice. So I don't remember off the top of my head the exact answer to your question.
Okay, thanks.
Okay. So an application of this that was sort of, I'm telling kind of the backward story. We first did the last slide on this thing, and then we tried to figure that out, and one slide back, and one slide back, and one slide back. So the reason I got it sort of, we wanted to be able to insert things on spheres is because something you'd really like to be able to do is insert morphisms on linked spheres, in particular on a kind of Hopf link. So here's a picture in 4D again of a two sphere linking a one sphere in the picture. I told you that there's this kind of canonical but kind of rich way to take simple things and put them on spheres. And so so if I take a simple K morphism, so a element of the base in the kind of, anyway, if you take a simple K morphism and a simple morphism of complementary dimension, you can put them on a pair of linked spheres, and this will evaluate to a number, just because by dimension counting. This is a sort of an application of a kind of a higher scheme theory. And a lemma or proposition is that this number doesn't actually depend on the simple morphisms you pick. It only depends on their class in homotopy. It only depends on their sort of Schur component class. And so this linking defines a matrix. It defines a matrix that pairs the kth homotopy group and the kind of co-kth homotopy group. That's a kind of number valued matrix. This is an analog for these quantum homotopy types that we're studying of a very classical piece of algebraic topology, which is the Whitehead bracket, Whitehead's Lie bracket on the homotopy groups of a topological space. I told you one construction of semisimple categories already. I waved at one construction given by linearization. Let me give another example that I won't tell you how it comes. I'll just tell you the answer to the example. So you could take n-dimensional digraph-Witten theory, for example. This is a gauge theory which exists in any dimension for any finite group. And you could take the operator contents of that n-dimensional digraph-Witten theory. When you study that example, you get a semisimple n category. In fact, a monoidal semisimple. Yeah, you get a semisimple n category. And you can work out what its homotopy groups are. And it turns out that all the homotopy groups are trivial except for two of them. So one of the non-trivial homotopy groups is the homotopy group in degree 2. And this turns out to be the conjugacy classes in the group. And the other non-trivial homotopy group, the only other one, is in degree n-1. So codimension, sort of if I'm in n dimensions. And those turn out to be the irreducible representations of the group. And quantum field theorists will recognize these. These irreducible representations, these are the simple line operators. And sure enough, if I have an operator, if I'm in degree n-1 in ambient dimension n, these are things that want to insert along lines. So these are the Wilson lines in this gauge theory. And these are the Atiyah surfaces in this gauge theory. These are things that, not surfaces, but kind of, these are the Atiyah operators in this gauge theory. These are the operators that insert a singularity of the gauge field. And if you work out what, for any digraph-Witten action, what the S matrix is, this kind of, you get the character table of the group. So the last thing I want to tell you about is to finish is sort of some of the things that we hope to do with this. So this Lie bracket, this Whitehead bracket, is I told you it's arising from a conjugation action. It's kind of telling you some commutator data for how operators commute if you're in the like the interpretation in terms of operators in a quantum field theory is that it's really a commutator of operators. And right, so this is sort of the last slide of my talk. So something you might know if you studied the character theory for a finite group is that the character table of a finite group turns out kind of to always be an invertible matrix, which is a really important part of studying finite group theory. And that invertibility seems to be true in general. And I'll just give the final theorem and then I'll end my talk. So I should have said earlier, there's a sort of some piece of it that maybe I'll end on. The theorem is that one of the things you can ask about is when your category is invertible, when it sort of is one-dimensional in some sense. And it turns out this could happen a lot. And that the category is invertible exactly when this S matrix is invertible. It's really measuring something really important. And for the quantum field theorists, the topological quantum field theorists in the audience, you might sort of use this as follows. So if you have an invertible category and a point in that category, that gives what somebody like Freyd and Telemon would call an anomalous quantum field theory, where the invertible category is playing the role of the anomaly. And conversely, the category itself in this correspondence, I mean, I should have almost said this is like a correspondent. There's a correspondence between kind of, this is C invertible. There turns out to be a correspondence between kind of invertible category and an object in it and anomalous quantum field theories, where the invertible category is the operators in that quantum field theory. The object X is just the sort of, the objects of the category are the space filling operators. They're the things that want to insert in codimension 0. The object X is the invisible space filling operator. And this invertibility ends up being really important if you wanted to study the classification of these. And I just want to end with an open question, which is that there's some non-trivial statements already for semi-simple 2 categories about when you really can do TQFT constructions, when you really have sufficient finiteness conditions. And so the conjecture is that semi-simple categories are always, so finite semi-simple categories always are sufficiently finite to do TQFT constructions, but this is a sort of non-trivial statement already when it is too. So, so there was a survey of this sort of new kind of quantum homotopy types that we're starting to develop. So thank you for all the questions, and I'm sure there will be more.
Well, thank you very much, Theo, for a lovely talk. And well, there is one question right now in the chat. So why don't we start with that? Vivek, can you unmute yourself?
Yeah, hi. I mean, this was just, I'm just trying to understand what you meant by anomalous QFT. So in physics, usually we study some number of dimensions, field theories with some number of dimensions. So can n just be any arbitrary integer here?
Yeah, I mean, it should be the category number of C.
I see, okay. Thanks.
Okay, well, Ezra has raised his hand.
Yeah, hi.
Ezra, good to see you.
I don't know. Did my video work? It doesn't look like it. I don't know why.
It did very briefly.
Don't see you, but we hear you fine.
Yeah.
Yes.
So I'm wondering, is the main reason that you're working with vector spaces over C that we're doing quantum mechanics, or some other reason? Because it occurs somehow in K theory, you can get a long way replacing abelian additive categories by Balthausen categories. So ultimately, the most important thing is that it's pointed. So I was wondering, how far could you get with a bunch of maybe co-limits and pointed?
So the reason I'm working over C is because in general, the theory of semi-simplicity is sort of hard, easiest in characteristic 0. And C is just, there's nothing special about C except that it's an algebraically closed characteristic 0 field. Some piece, so the reason this is a conjecture is that this is for instance, known but not easy for 2 categories, and it uses that some that certain integer matrix, a certain kind of positive integer valued matrix, has a kind of positive eigenvalue. So it's really using some, the proof of a conjecture like this really uses something special, like something about the real numbers and about positivity. So there is sort of a little bit of there's some analysis that shows a role. As to your more general question about K-theory and Waldhausen categories, I think the answer is that we're too early in the development of the subject to be able to address it.
Great,
So
thanks.
sort of investigating very finite objects.
Right.
Okay, Marco, you're next.
Hey, Theo, thanks for your talk. I was just wondering, so I'm just curious about this terminology of quantum homotopy type. So if I think of a simplicial set, let's say, as giving me a homotopy type,
right?
What am I supposed to think of as a quantum homotopy type? What would be an associated quantum homotopy type?
So I'll repeat something I said at the very beginning, which is this all very much I'm reporting things in progress. Right. And we have a sort of, so far, I think we have, I don't think we feel like we have an actual definition of quantum homotopy type. I think what we have is the strong intuition that that's what these feel like. We do have some ways of thinking of these categories as like simplicial sets or cell complexes. I drew some of those on the early slides where I was sort of drawing a picture of the skeletonization.
Would you say that, for example, like in the case of simplicial sets, right? We at each level we have a set, a finite set, suppose.
That's right.
And we don't have a notion of direct sum. We don't take linear combinations of these points. Is that roughly what you're thinking of, or what? How should I? So
one thing I'm thinking of is lots of constructions from algebraic topology should have, I expect to have generalizations. I expect there to be a good theory of skeleton, of Poincare towers, of these things. And there's a one-way street that I told you, given a homotopy type in the usual sense, there's a linearization that produces one of these. But you're asking a sort of better question, which is like, how close to topology is this? And the answer is, there is a way, if you take if I start with a semi-simple category, I could say, look at its Schur components and take one representative object from each Schur component. And I'm going to start building basically a space for you. I'll put a point down for every object. Now I can look at the kind of loop category of each of those objects, and I can put a morphism, and it has its own components. So let me pick representatives. I'll just pick them. And I'll put a one morphism down for each of my choices.
Okay.
Now you can start looking at kind of composable tuples of morphisms, or rather at kind of closed composable loops of morphisms. And look at kind of the category of ways to fill, or the, I guess, n-2 category of ways to fill any sphere. So sorry, for any circle now, so I've built so far for you, I've built a one skeleton. It had some points and some lines. Now for any circle in my one skeleton, there's a category of ways to fill that circle. It doesn't matter where you start along the circle for some dualizability reasons. I can look at the n-2 category of fillings for that circle. And I can choose representatives of its homotopy, and I'll glue those two cells in. And I can keep going, and I can then build an actual cell complex from these choices. The answer I get does depend on the cell complex. And I don't think we have a kind of nice, clean statement that says that gives you a recognition for when two cell complexes give the same category. Did that answer the question or not?
It's pointing me in the right direction. Thanks.
Okay.
So Aaron Debray has been patiently waiting on the chat. Maybe can you unmute yourself?
Thanks. So first, Theo, thanks for giving a really cool talk. I wanted to ask about this last theorem on this slide, which says that roughly, I think you understand what the invertible objects in this symmetric modal n category are, or n+1 category.
I would say we have a recognition principle for them.
Great. How much does this tell us about the homotopy type of the Picard's subgroupoid of invertible objects?
Very little.
I see.
Because what happens, and what I didn't have time to tell you, was that it can often happen. So I did tell you that it often happens that simple things which are not isomorphic are nevertheless sort of Schur connected. They represent the same homotopy class. Mm-hmm. if you have an invertible thing, it's certainly simple, but the opposite, but most simple things are not invertible, but invertible things are definitely simple. It often happens that invertible things, which are not isomorphic, nevertheless represent the same homotopy class. And so there's a massive loss of information from past, like there's sort of these two really different things. You can take the Schur components, or you can pass to the invertibles, and that's a space, and you can take its actual components in the sense of topology. And these are two very different pictures of the whole category. And they seem to have somewhat complementary information, but I don't have anything sharp to say exactly for what, like, for the complementary information. I just say in examples, they seem to see really different features of the category.
Okay, thank you. That was a very helpful answer.
Let's go to Greg Moe, has his hands up.
Yeah. So we're familiar with from topological defects having framings from Chern-Simons theory. Yeah, I think part of what you're doing is generalizing them. And I was wondering what we have to say about framings when we're taking operator product expansions or fusion products of defects, say parallel defects. So I mean, I know a little bit about that from the line defects in Chern-Simons theory, and it's not totally trivial. And so there's no obvious way, I think, of adding framing.
Right. Well, the most general thing, which is the only thing I'm kind of fairly confident of, is that this is a good question. So the most general thing that the only thing I'm really confident of is that in general, if I didn't have semi-simplicity around, then the insertion rule from the perspective of category theory, what Lurie tells us the insertion rule is, what he kind of sketches a proof, proves at the level of rigor that my talk is at, certainly, is that the rule is that I need a normal framing and a tangential framing and a compatibility equivalence between those.
Okay.
And if you take two operators and bring them, if you take two kind of, and this is a monoidal thing you can do. I'm being told my internet connection is unstable. I hope you don't lose me. So if you bring two surfaces together that have where all of that data exactly matches, then I know you can take an operator product of those. If the data doesn't match, I don't know what to do. Okay. I suspect in the semi-simple world, you just don't need all this tangential framing data.
Okay, that's actually similar to the story with Wilson lines that I do know. I mean, in general, if you take just two randomly framed Wilson lines and try and take their fusion product, it doesn't make a whole lot of sense. You have to have compatible framing. So, but now I have a follow-up question though, which is, so there are claims in the literature that you could take fusion products of these topological defects and on the right-hand side get higher codimension defects, which I don't understand it very well, but it's sort of a two-part question. A, is that part of your theory? And B, how would the framings work in that case? Because it seems like you need even more.
I don't know the answer to B.
A higher codimension defect. Okay, so for an example is a recent paper.
I don't know the answer to B. Go ahead.
No.
Well, anyway, so I'm sorry. The internet got patchy for a moment. Can you guys hear me?
Yes, we can hear you.
Maybe you can. Maybe. Okay. I don't know the answer to B at all because it's not something I've thought about. I don't think I would have anything to say right now that's not somehow implicit in what Lurie tells us. And although I suspect under the semi-simplicity that you need less data, that was sort of the point of this slide in a subtle way. If you do have all of this kind of framing data then I don't know. The time I know that you can produce higher dimensional defects is once you've chosen skeletal information, once you've chosen representative operators to kind of give you a coordinates. Then higher dimensional operators arise as like a change of basis information between different skeletalizations. Like these two things, it's not exactly equal to something else, but it's equal up to a higher defect,
Maybe just to be concrete, in a four-dimensional theory, I mean, there are papers claiming that you can take a fusion product of two surface defects and get a sum of line defects. Does that make sense to you?
If I saw that claim, I haven't seen such papers myself because I don't know, I haven't sort of investigated, but if you told me that, and if we were sort of hanging out in the lounge, I would understand you as meaning that you had secretly chosen representatives for every surface operator, and that the line defect was arising from the failure of the representatives to be quite compatible.
I see, okay. To respond to the chat question, I'm talking about a paper. That would be
my interpretation of it.
I'm talking about a paper with many authors. I don't remember them all. It involves Rees, Heidenreich, Valenzuela from Harvard about generalized symmetries. And they have thank you, Sakura. And they have an example of OQ gauge theory with the product of surface defect that has a line defect in its fusion multiple.
I haven't looked at that. I haven't studied that paper, so I can't really comment on it.
Let's go to Kevin.
Yeah, so hopefully this is an easy question. So in like n equals 2 or our favorite subcases of n equals 3, what does your semi-simple definition boil down to in more traditional category language?
So one of the basic structure theorems that Chris Douglas and David Reutter prove is that finite semi-simple 2 category is always the module theory for a multi-fusion 1 category. So talking about finite semi-simple 2 categories is the same as talking about fusion categories up to Morita equivalence. Or multi-fusion categories, I should say, up to Morita equivalence. Is that what you're looking for?
Yeah, it's something like it. And I guess a follow-up question, would you expect there to be some theorem that, given an n category, you can build out a full TQFT if and only if it's semi-simple? Is that a test for your students?
What I expect is I should say this carefully. So there's questions about whether something can arise from a TQFT construction, whether something becomes a fully extended TQFT. These questions depend sensitively on what type of tensor product you're using in your ambient environment. So there's sort of different higher categorical linear algebras, and it can a priori depend on that. That said, in the case of it can depend on whether you're in, what the ambient kind of tensor sort of n linear algebra you're working at a priori. When in the case of 2-dimensional CQFTs, we have a very good list, there's a long list of reasonable types of 2 categorical linear algebra. And they have the feature that they all have the same fully dualizable objects. They all have the same fully extended TQFTs among them. They have different, not quite fully extended TQFTs. So they have different, say, 2 plus epsilon dimensional TQFTs or 1 plus epsilon dimensional TQFTs. But they have the same list of fully extended TQFTs. And I expect a statement like that to be true in general for other n. And yes, I expect that in characteristic 0, the categories that are fully dualizable are precisely the finite semi-simple ones. And in characteristic P, I would expect there to be a theory of dimensions and the dimension, then some statement about the dimension being non-zero. But I don't know any of those as theorems.
Okay, thanks. So the next question is from Sasha Vonov.
Hi. Yeah, thank you for the talk, Theo. Actually, I have a question related to the Whitehead brackets.
Yes.
In topology, the Whitehead bracket can be nicely realized on the loop space of the space, and by using the concatenation of loops and the associated commutator map. It's called,
Yes.
I think it's called the Samuelson product. Is there anything analogous to this in this n-category framework?
I would hope so, but I don't have one.
Okay.
Because I only know right now how to do it with simple objects.
Mm-hmm. Okay. Well, yeah, in topology, so it's also you also are using the commutator map, so it's really you're
Yes.
using inverses. Yeah.
That's right. And so this is, so what I have is I have a way of relaxing the need for inverses, but only when you have simple objects. And the problem is that kind of the simple objects, like there's some sort of, there are non-invertible things between simple objects, and there's also non-simple things between simple objects, and I don't know how to extend to those.
Okay. So, thank
but
you.
I would hope so. I mean, there's something close to that like somehow what it feels like is that the sort of there's like the quantum homotopy type is somehow the collection of all simples with simple maps between them and simple maps between those. Those are the cells in the quantum homotopy type. I expect this type of construction to sort of make sense at the level of quantum homotopy types, but I only know how to do it on homotopy itself right now.
I see. Thank you.
Are there any further questions? I think we've exhausted the audience and our speaker, so let's thank Theo again for a great talk. Thank you very much.
Thank you for having me.
Okay, so till we meet again.